Welcome to lesson 3.7. Today we're going to look at determining an empirical formula. The first few slides talk about the process that chemists use to work backwards and determine the actual empirical and then molecular formula of a compound. As a student in general chemistry, you're not going to do this, so these are basically kind of for your reference, like how does this really work in real life kind of slides. So they'll actually get the weight of the compound that they're going to examine, and then they're going to send that particular compound, because most of the time we're talking about an organic compound that'll combust, and so we're going to send it through a combustion process. They'll so the sample will burn, the water will come off and be collected in an absorber, and the carbon dioxide will also be collected in an absorber. Anything else will be released. They use that organic compound to find the water and the carbon dioxide, so they can figure out how much carbon and how much hydrogen is in the compound. If it was a more complex compound with several more elements, they would have to use a different process to figure out what the other elements were and how much of them there were. But anyway, an empirical formula is the smallest whole number ratio of the atoms in a formula. An empirical formula of an ionic compound is equal to the formula of that ionic compound, because by definition, ionic compound is the smallest whole number ratio of the ions that go to their combining ability in terms of charges. But in a covalent compound, the empirical formula can then be used to help determine the molecular formula. So for example, here, this empirical formula is CH5N, but I could take that may be a multiple of any integer in order to figure out what the molecular formula is. And so in order to determine the molecular formula, you need the molar mass of the molecule. Most empirical formula calculations are based off percentages, and so what we do is we just assume we have 100 grams of the compound. We could assume we have a different number of grams, but it's much easier to take 50% and say we have 50 grams than it is to say, okay, let's pretend we're starting off with 25 grams. Well, then you need to take each of those percentages times 25. So much easier to take them times 100. So that's why we use 100. We would get the same result if we used a different mass, because the percentages would be equivalent. In chemistry, anytime we have a unit that's not moles, it works best if we convert it to moles, because that's the universal language of chemistry. And so we'll use the molar mass, or the atomic weight of each element, to determine how many moles of each element is represented by that mass that we obtain from our 100-gram sample. I mentioned this earlier. What would happen if we chose another mass? It would still work. Once we've obtained the empirical formula, we can figure out what the molecular formula is based off of this particular calculation. So you'll be given the molar mass of the molecular formula. You determine the empirical formula mass by first determining the empirical formula and then adding the elements up to determine what that is. You should get a whole number out here, and then that whole number will be multiplied times the empirical formula. So I know that's a lot of talking through problems, and talking through problems it can be kind of confusing, so let's go ahead and look at an example. In this, we have a white powder that was analyzed, and it only has two elements in it. It has phosphorus and it has oxygen. 43.64% phosphorus and 56.36% oxygen. And then it tells us it has a molar mass of 283.88. So we are going to wait to use this number till later, but we're going to figure out what the empirical formula is. Now, when you're determining empirical formulas, it's important that you use as much of a mass number as you're given. So, for example, we're going to start off here with phosphorus, and we have percentages. We're going to pretend we have 100 grams, so we have 43.64 grams of phosphorus. From the periodic table, phosphorus has a molar mass of 30.6 3.974 grams in 1 mole. Okay, I'm going to put that into my calculator, and I find that 43.64 grams of phosphorus is equivalent to 1.4, and I'm going to keep several numbers here after the decimal, 4089 moles. Okay, we're going to do the same thing with oxygen, 56.36 grams of oxygen. And oxygen on the periodic table has a mass of 15.999 grams in 1 mole. So 56.36 divided by 15.999 gives me an answer of 3.5227. Now, what this tells me is that's the number of moles we would have of phosphorus and of oxygen if we had a 100-gram sample. That doesn't tell me what the formula is. I have to do what we call a mole ratio. So to do a mole ratio, simply figure out which one's the smallest number. That's 1.4089. And you divide both by 1.4089. Slip through this. And there we have the calculations that are in the PowerPoint. Notice they didn't use the complete masses that are on the periodic table. I think you get better results if you do. Divide each of those by the smaller, so we get 1. The ratio of phosphorus is 1. The ratio of oxygen is 2.5. So if you put that in a formula, you would get P1O 2.5. Well, we can't have that formula because we have to have whole numbers as subscripts. And so our formula is actually P2O5. So that is our empirical formula. That's the smallest whole number ratio of where those two nonmetal atoms fit together in this particular compound. So the molecular formula of the compound, what we have to do is we have to calculate the empirical mass. And this you can kind of do. You don't necessarily have to use the whole mass. So let's go ahead and look at P2O5. Phosphorus. So we have 2 phosphorus. Each of those has a mass of 31, basically. And then we have 5 oxygens. Each of those has a mass of about 16. And so if we calculate the molar mass, we get about 142. Okay. In our prompt, it said our given molar mass was 283.88. So molar mass given in the problem divided by the calculated empirical mass. And we come up with 1.999, which basically equals 2. And so we will take our empirical formula and take each of those subscripts times 2, and this is the molecular formula of our compound. There's the structural formula for that compound. Here is another example. I suggest you pause the video and work through this example before you look at the answer. Just again, kind of working through how you determine molecular formula. Another example. So this is asking for the molecular formula of caffeine. So again, you're going to work through, you have carbon, hydrogen, nitrogen, oxygen. And this one gives you a step-by-step of that. get those integers. And then this last one, you'll often see these on the test where it'll give you an empirical formula. And then it gives you a molar mass. So basically what I'm going to do is I'm going to take the molar mass, basically 104. The mass of this is 12 plus 1, or 13. So if I take 104 and I divide it by 13, I get 8. And so that means this is the correct molecular formula. I encourage you to work through several empirical formula examples. You can probably find some at the end of the chapter in your book. There will be some in the homework. Do practice this concept, because if you don't practice it on your own, it is hard to understand. So until next time, where we start looking at chemical equations.